Hey y'all, today we're going to begin our discussion on Gibbs free energy. We're just going to do a brief overview today, and then tomorrow we'll get into some calculations of how we use Gibbs free energy. And so we talked about Gibbs free energy briefly during the first lesson, but just as a reminder, Gibbs free energy has a symbol of G, and what we will be calculating is delta G as we go through this. So we'll be looking at the change in the free energy over the course of a process. But remember, Gibbs free energy is just the energy associated with the process that can be used to do work. Okay, and so now, if we look at a process and we see that the delta G is negative for that process, that just means that the system is releasing energy so that we can do work on the surroundings. And so really, if we look at a plot for Gibbs free energy, it kind of looks different than a plot for enthalpy change, because kind of Gibbs free energy kind of looks like it decreases when we go from a reactance, and then it'll go and start to increase to get to our products. A cool thing to remember about this, right, is like in this particular case, we see that Gibbs free energy decreases, right? So here we would see Gibbs free energy, the change delta G would be equaling a negative sign, right? So we have that loss of free energy. And the great thing about this, when I look at this graph, it kind of makes me chuckle, is like, let's imagine there's a rock. Make that circle bigger. Let's imagine that there's a rock right there. And let's imagine there's some poor soul standing down here, right? If Gibbs free energy is negative, which means that the products have a lower free energy than the reactants. What that means is, like, if I look at that rock and that rock comes down the hill, it's pretty much going to take out that person, right? We're not going to have to do anything to that rock to get it to take out that person. That rock will work over that person, right? We didn't have to do anything to it. And remember, if we have a process that we don't have to do any work to, that process is going to be spontaneous. And so if Gibbs free energy, or delta G for a process, is negative, the process will be spontaneous, right? So if delta G is negative, the process is going to be spontaneous. Always. There's no exception to that. Okay? Now, conversely, if I'm thinking about, okay, well, what happens if delta G is positive, right? And so in this case here, if delta G is positive, that means that basically we have to do work on the system to get the process to occur. So if we go back to our little analogy, and I have my rock here, and I have my person here, right? This rock is not going to be able to get up that hill to hit that person, right? If we wanted to hit that person, we're going to have to actually push it up the hill in order to get there. And so we have to do work to get it up that hill because delta G is positive. So anytime that we see delta G being positive, the process will not be spontaneous, right? And again, that is true, right? There's no exceptions to that. Delta G is negative, we're spontaneous. Delta G is positive, we are not going to be spontaneous, or we're going to be non-spontaneous. The other thing to this is, well, what happens if delta G is 0, right? So delta G is 0, then that basic process is going to be at equilibrium. And so kind of think about this, we have that rock there, and if that rock kind of goes down, right, it's going to be able to go back up. It is going to get up to exactly the same spot, right? And if we say there's no friction or anything else, that ball will just kind of keep rolling back and forth, right, without any work being done to it. But we're not kind of gaining or losing anything. So at that point in time, delta G is negative because it's doing work, but then it's having work done on it back and forth. And so at that point in time, we say that process is at equilibrium. So it's really important for us to remember that when delta G equals 0 for a process, we are going to be at equilibrium. Okay? Now, we just spent the first part of this unit talking about enthalpy changes and entropy changes and how they relate to the spontaneity of things and how we calculate them. And it seems really weird because now, well, why don't we just figure out delta G for a process? Well, unfortunately, finding delta G for a process isn't all that easy. It's much easier to calculate delta H and delta S for a process. And so here's the thing, right? How do these things come into play? Well, we know the natural tendency of things for a particular process, if we're talking about enthalpy, right, our delta H, is that reactions tend to want to be exothermic, right? If they're exothermic, the bonds in the products are more stable than the bonds in the reactants. And that's what we want, right? That's why chemical reactions tend to happen, because things want to become more stable. But also we learn through the second law of thermodynamics that things also want to become more random, right? And so ideally we would have a process that is exothermic and becoming more random. So delta H is negative, delta S is positive. And in that particular case, what we know is that delta G will always be negative, right? So if delta H is positive, delta H is negative and delta S is positive, delta G is always going to be negative, and this process will always be spontaneous. Okay, it doesn't matter how big those values are, but if delta H is negative, delta S is positive, the process is going to be spontaneous. Conversely, right, if that process is endothermic, so those bonds are becoming less stable, right, and delta S is negative, so the process is becoming more random, you can probably guess that, well, that's not really what nature wants to do. And so that process is going to have a positive delta G, right? We're going to have to do work to that process to get it happen. And so this process, while it can happen, will never happen spontaneously, right? And that is always the case, right? It is always going to be a no in terms, is it spontaneous? No, that's always the case if H is positive and S is negative. Now, where things can get a little complicated is it is very much possible to have delta H be positive and delta S be positive, right? Prime example is melting ice, right? If we have solid ice and we want it to go to a liquid, right? We know that this is endothermic. We have to take in heat to break up those bonds, but now we also know that delta S for this is positive because we're going from that more ordered state to a less ordered state. So in this case here, boom, boom. Well, in this particular case, what's going to happen? Well, we know ice melts sometimes, but it doesn't at other times, right? So we know ice will melt at 25 degrees C if we put it on there, but if we put it in the freezer, is the ice going to melt? Not so much. So in this particular case, delta G can be negative or positive, and in this case here, it's going to depend on the temperature, right? And just as I said, in this particular case, where does it tend to be spontaneous? Well, it's going to be more spontaneous at higher temperatures than lower temperatures. Ice will melt at 25 degrees C, but it will not melt at -10, right? And so in this case here, we know it's going to be spontaneous at higher temps. And so since it's spontaneous at higher temps, we know at higher temps, entropy is going to be delta S. Entropy is going to be the driving force, where if it's at a lower temperature, then the enthalpy is going to be the driving force. The same thing can be said if we have an exothermic reaction, but that exothermic reaction happens to be becoming more ordered. So in this case here, we have delta H and delta S being both negative. Again, it's going to be dependent on temperature, whether or not it's going to be spontaneous. And so it's going to be depend on the temp. And we know in this case, it'll be spontaneous at lower temps. Okay, so we can see that in this particular case, that sometimes, no matter what the temperature, a process can be spontaneous or it can be non-spontaneous, but in other situations, it's going to depend on the temperature. And so you can see there's a relationship between delta H, delta G, and delta S. And so, and there is fortunately a mathematical relationship that we're going to start using tomorrow. And that mathematical relationship is pretty simple. It's basically delta G, well, that is not a G. It's going to be delta G is going to be equal to delta H minus T delta S. Okay, so notice that delta H is not really affected by temperature because the bonds that are broken and formed are not affected by temperature. All right, so the type of bonds that we have. However, we can see that entropy is definitely affected by temperature, and we know that that's the whole point of entropy, right? Third law tells us it's zero at 0 Kelvin, and then we know that it will go up from there and change from there. So in this particular case, we know entropy changes with temp. Okay, so we have to take the temperature into consideration when we're dealing with delta S. Okay, and so that's why it's delta H minus T delta S. All right, so tomorrow what we're going to do is we're going to look at this equation and how we can use it in calculations to figure out what delta G is in certain situations, and then look at delta G in other situations such as, how can we use delta G to figure out the equilibrium constant of a reaction? And that'll be fun. All right, guys, I hope you're doing well. Hang in there. We're almost done with week 2. And I will chat at you later. Pop in the office hours if you need me. All right, guys. Peace, love, happiness. Thanks for playing.